All right, so like we talked about in the last video, it is possible to get skewed data or a skewed distribution, and that is when you end up with scores in your data set that are extreme, either extremely high or extremely low. And so scientists use something called a standard deviation in order to help them understand actually how big or small that skew might be. In other words, how much do averages how much do scores deviate from the mean, the average? All right, so let's talk about that. How do we do that? We do that using measures of variation. And this picture here is called the normal curve or the normal distribution, this right here. This is a distribution or a curve. It's also sometimes called the bell curve. You'll see that sometimes as well. And it describes the distribution of many types of data where most scores fall near the mean, okay? So average intelligence is one of those. Average height, average weight, average grades. There's typically only a finite amount of heights that a human can be, and most fall within, let's say, 9 inches of each other, okay? Average height, same thing, average weight. Even with intelligence on an intelligence score, you're not going to have that much variation. Yes, you're going to have people that score extremely high and extremely low, but they're going to be by and large in the minority of your data set. Okay, so we use this bell curve to find standard deviation. Good news for you is that you don't need to calculate standard deviation. You just need to know how to understand standard deviation. So standard deviation, can I say that more times? I don't think so, is a computed measure of how much scores vary around the mean score. In other words, what's the spread, okay? And we're going to dive into that in a second, okay? So having a standard deviation is sometimes superior to just having the mean mode median. Because it gauges if your scores are packed together, i.e. they're very close to the mean, mode, and median, or they vary in uniformity from each other. So let's check it out. So this is a bell curve, a normal distribution of the Wechsler. This is the Wechsler intelligence score, and as we can see here, the average score is 100, okay? And this particular distribution has a standard deviation of 15, okay? So what we can see here from this bell curve, from the data set, is that 68% of people are within one standard deviation, okay, using the 15 points here. They're within one standard deviation of the mean, which is 100, okay? So 34% of people scored a 115, 34% of people scored an 85, but by and large, 68% of our population scored within one standard deviation to the average, which is 100, okay? As we move out this way to our second, standard deviation set, we see that it's actually 95 people that fall within these scores, okay? So standard deviation kind of breaks down the data in a unique way using a formula, so that way we can see where most people are, okay? In a normal bell curve, 68% of people are going to be within one standard deviation above or below your average, okay? So do look at that. Know that you will not have to measure standard deviation, but you will need to understand a chart like this. So do look at it again in your book, okay? All right, let's talk inferential statistics. So remember that inferential statistics are numerical data that allows us to generalize or infer from the sample data to the probability of something being true of a population. So that word infer with inferential statistics is really important, okay? And we're looking here, inferential statistics, in order to apply it to a population, they need to be reliable. And there's a few things that help to make a particular data set more or less reliable, okay? Having a representative population makes your data more reliable than if you had to buy a sample. Having less variability in scores makes your data more reliable than if you had a lot of variation in your data. And having more cases is always better than a few, right? So for instance, if you were a prospective student coming to Carondelet or De La Salle and you based your opinion by coming and sitting in one class, that's not a very strong case. You just saw one teacher. They could have been fantastic or mediocre or bad, and you would have formed your whole opinion about the school based on that one class you sat in on. So the more cases, the more times you run data, the stronger you can make inferences, the more reliable your data is. All right, so with inferential statistics, there are two types of errors, okay? And you should get these in your notes. They're not in the book. However, it might come up. It's totally possible. So how sure are we that our results are what we think they are? In an ideal world, our results are what we think they are, right? We say, we come up with a data point, we infer it to a population, and we're right. But there's also two types of errors. So there's a type 1 error, which is a false positive, noted here by the man being told that he's pregnant. So sometimes we might think that we find something when really it doesn't exist, okay? Or a type 2 error where it's a false negative. In order, something is there, but we failed to see it, okay? So get those two types of errors in your notes. I don't think it will come up a ton, but it is totally possible. All right, so in inferential statistics, we're looking for statistical significance, and statistical significance is the threshold at which we can say this is mathematically sound enough to be able to draw some conclusions about some information that we've gathered. So in the book, they talked about levels of aggression between men and women, and they inferred based on their statistics that men are more aggressive than women, right? But did they get a big enough sample? Did they make sure that their findings were not just due to chance? Did they make sure that they had similar types of people who were part of the study, or a diverse enough population to be part of the study? So it's important that if you're going to say something is true about a large population, i.e. men are more aggressive than women, that you make sure that you have enough statistical significance in order to be able to draw those conclusions. So like I said, you're not going to need to know how to calculate anything like the standard deviation or a p-value, but what I need you to know, and what's not in the book about inferential statistics, is that when data analysts run data for inferential statistics, they end up with a p-value, okay? This is important, and like I said, it's not in your book, okay? The p-value represents the chance of error. So a p-value could be anywhere between 0 to 1. Okay, 0 meaning there's absolutely no chance of error. 1 being is you are 100%, your data is full of errors. Okay, so like I said, you don't need to be able to calculate that, but you do need to be able to look at a p-score and understand, is there statistical significance or not? Okay, the smaller the p-value, the closer it is to 0, the more statistically significant your results are, okay? In the field of psychology, your p has to be less than 0.05, meaning there's a 95% chance that your study's results are not due to chance or not due to randomness, okay? So a p-score of 0 is impossible. It's impossible to be 100% sure, but in order to really get your data published as a social psychologist, your p-value of the statistics that you run would need to be 0.05 or less, meaning that you have 95% chance or higher of your results not being due to chance. Okay, so that's really important. So do be ready to look at a p-score and describe to me if that social scientist can now use the data to make an inference about a population. All right, so let's look at something that you might get from a test from me or on the AP test that has to do with a p-value, okay? So I got this actually from those psych videos that the College Board put out for review for last year, so you can actually watch these yourself. So let's read it. Mr. Reed taught one of his classes online and another one in person to see if there was a difference in test scores. He did some calculations, which like I said, you're not going to have to know how to do, and isn't sure if the difference between the results is significant. His p-value was 0.07. Is the difference significant? All right, so his P is 0.7, which means that his level of uncertainty is 7%. So he can say with 93% certainty that his results are not due to chance. So that's really high. But if you remember from the slide behind us, that the p-score has to be less than 0.5 to be statistically significant in order to be able to publish those results and make a claim. So while Mr. Reed has a high level of certainty, it's not high enough in order to be statistically significant, okay? So do know that, and try not to get the p-value, which is 0 through 1, confused with correlation. And remember, correlation is between -1 and 1. So we'll do some practice with that, but make sure that you know your correlation score scale and you know your p-value scale, okay? All right, thanks everyone.